Okay, thank you so much. Okay, as it is mentioned that we already finished the compressible flow topic, okay, which is the previous in the previous lecture we already discussed problems. Okay, so that the course of compressible flow. So it is at the same topic which we covered in the last lecture. Okay, so now here it is a new topic which is the rotodynamic machinery. Okay, so this is not from your book. Okay, so I will use different references. Okay, so it is basically the purpose of this chapter, or you can say this lecture, is just to introduce that how your rotodynamic machinery, what are the type of rotodynamic machinery, and then how you can analyze different, for example, parameters related to rotodynamic machinery and specifically to the steam power plants. Okay, because rotodynamic machinery are many kinds. It is used in the hydraulic also. It is used in the different power plants which is working on the fluid machinery. Okay, so here we only talk about the steam rotodynamic machinery. Okay, so here the question is where is the rotodynamic machinery in our specific power plants or in our daily life power plant? Basically, the turbines, which we already discussed in many times, either it will be the gas power plants or either it is steam power plants. So these turbines basically are the rotodynamic machines. Okay, because if you can notice that these convert some rotary machinery, rotary motion into some sort of other useful work. Okay, so that's why in your steam power plant, you can say these are the rotodynamic machine, and which is used in order to run the generator. Okay, that was attached to the turbines. Okay, so if you can just take a look for the specific definition of the rotodynamic machine, so in which the fluid flow freely through an impeller or a rotor. Okay, and the transfer of energy between the fluid and the rotor is continuous, and the change of angular momentum of the fluid causes or is the result of a torque on the rotor. Okay, this is just a basic definition of rotodynamic machines. Okay, so the main component for your steam power plants are the steam turbines, because that was the main unit where you have to convert, or where you have to supply some sort of motion to your other machine. Okay, that will be converted into some useful work. Okay, so first important point, that steam turbine is a prime mover in which work is obtained by gradual change in momentum of steam. Okay, so what is the meaning of prime mover in this statement? So basically, prime mover is any device which supplies some sort of you can say motion, okay, to other machinery. Okay, so for example, your steam turbine, the main purpose of your steam turbine is to produce some rotary motion, and that rotary motion will be transferred to your generator, and then the generator will produce some useful work. Okay, so in this case, our steam turbine is a prime mover. Okay, because that is the main source where you are supplying your rotary motion to other part of the to other machineries. Okay, so that is the prime mover. So if I just take a simple definition of prime mover, so for example, in your daily uses, you use the fan in your houses. Okay, so your fan basically is rotating by using motor. Okay, so in the case of fan, the motor is the prime mover. Or if you can take the example of your pumps, okay, that was the pumps you can daily use to throw the water from low height to upper height. Okay, so in that case also your motor is the prime mover, because motor is attached with the pump. Okay, so motor is basically your prime mover. So in the case of steam turbines, your in case of power plants, your steam turbine is basically the prime mover. Okay, so this is just a basic definition that the steam turbines is a prime mover. Okay, so I already told you that in your turbine, when we are looking for the Brayton cycle lecture, that in your turbines there are different type of blades. Okay, and that blades are a combination of your stationary blades, and also there's a moving blade. Okay, so basically, all your steam which you make from the boiler or which is extracted from the boiler sent to the turbine section, and that will be thrown to the turbine. Okay, so to produce some sort of useful work. Okay, and from Newton's second law, the rate of change of momentum is equal to net force. So this is basically a simple you can say principle behind your steam turbines, that if you can throw steam on your blades, that was the stationary or the moving blade. Okay, so then that motion or that steam, the kinetic energy which is carried from that steam will be converted, or you can say send it to your different section of blades, and then as a result that blade moves, and then due to, and this these blades are attached to single shaft. Okay, that was the common shaft we already discussed in the gas power plant section. Okay, so that is just a basic principle, and the change in velocity can be due to change in magnitude or velocity. Okay, so what is the meaning of this? So here there are two figures, figure A and figure B. Okay, so in the figure A, if you can notice, there is a straight wall, and this is your nozzle. Okay, so for example, this is nozzle, and you can say that steam is coming out of this nozzle, and at this wall, this is your, you can say, stagnation point. V2 is equal to 0. Okay, and the force that is exerted due to this steam that is coming from towards this wall is basically impulse force. Okay, so impulse force, I hope to already know the definition of impulse force. And as a result, if this is a stationary wall, so the impulse force is equal to mass, that is the mass of your steam or your mass flow rate, into V1. Okay, so V1 is basically the velocity that is for the steam. Okay, similarly, if we just take that an example, there is a curved body. Okay, so in the second figure, if you can notice, instead of straight wall, we have the curved shape, something you can say just a curved wall. Okay, and we just throw some steam from one side of this wall and through the nozzle, and with the velocity v1. Okay, and you can say this is the stationary wall. Okay, and the impulse force that is acting upon it will be equal to m v1 minus v2. So in this case, your v2 is basically minus v1, because if you can notice, if we, I can just assume that the surface of this curved body is frictionless. Okay, so the velocity that is coming out of it is equal to minus v1. Okay, so in this case, your impulse force become 2m v1. Okay, so same principle we use in the steam turbines, because in order to run the steam turbine by using the different blade section. So our main target is to produce that impulse force, and that impulse force will cause the rotation of your blade. Okay, so this is the basic principle of your turbines. So a steam turbine is a device that extracts thermal energy from pressurized steam and use it to do mechanical work on a rotating output shaft. So working principle, we already know that the generation of high velocity steam jet by the expansion of high pressure steam and then conversion of kinetic energy so obtained into mechanical work or on the rotor blades. So steam turbines basically consist of main parts. Okay, as there is many parts of the steam turbine, but the main parts are the fixed nozzle and moving curved blade. Okay, so here important point is curved blade, because if we cannot make the blade curved, so we cannot generate an impulse force. Okay, and then it will not result in the you can say rotation of your blade. Okay, so a high velocity jet coming out of steam nozzle impinges on curved blade. Blade are so curved that steam enter without any shock. Steam glide tangentially on the curved blade, fixed to the periphery of the moving blade. Blades start to move due to change in direction of flowing steam, and a steam turbine convert high pressure steam from steam boiler into high velocity steam jet and steam nozzle, and convert high energy of steam into mechanical work by changing direction of steam flow in the moving blade. Okay, so we will look one video as well. Okay, so that you will get some understanding. So right now you just have to uh, go through it, all the theory. So steam turbines are used in power plants to derive electric generator to propel large ships, submarine, to derive fans, compressor, and pumps. So these are some application of your steam turbines. Okay, so this is basic steam turbine. Okay, I hope you already know that what are the basic components that in the steam turbine. So in the steam turbine, we have different type of turbines attached to the single state shaft. Okay, so for example, this is your single state shaft, and at this shaft, if you can notice that there is a high pressure turbine, there is a intermediate pressure turbine, there is a low pressure turbine, and all the turbines have some blades. Okay, so if you can notice, all the turbines have some blade, and which is enclosed in the casing. Okay, and this is your rotor, and then there is a nozzle. Okay, and this nozzle will impinge your steam to the high pressure turbine, and then that same energy transferred to your intermediate pressure turbine, and then low pressure turbine, and then at the end you will send this energy to the generator to run the generator. So this is just a basic steam turbine. Okay, so then based on the classification, your turbine is classified in many types. Okay, but the main types that we discuss in this lecture is according to mode of action. So according to mode of action, there are two turbines: impulse turbine and reaction turbine. Okay, so same turbines are used in the hydraulic machinery as well, or you can say fluid machinery. Okay, where you convert some fluid motion into some other sort of useful work, or same turbines used in the steam power plants as well. So according to direction of steam flow, so there is axial flow turbine, radial flow turbine. According to exhaust condition of steam, there is a condensing turbine, there is non-condensing turbine. Then according to pressure of steam at inlet to turbine, we have low pressure turbine, medium pressure turbine, and high pressure turbine. And according to number of stages, we have single stage turbine and multi-stage turbine. So basically, stage turbine means that we have different set of blades. So if we have one fixed set of blades and one rotating set of blade, so it's mean it has single stage. And for example, if we have two set of blades, okay, which each consists of single blade, which is non-rotating, and there is a moving blade, so it is called the multi-stage turbine. Okay, so in this lecture, we will talk about these two turbine, which is impulse turbine and reaction turbine, and how we can analyze different parameters for the impulse and the reaction turbines. Okay, so impulse turbine, basically it is shown over there as well in the figure. So impulse turbine work on basis of Newton's second law of motion, that is change in momentum produces force. In this turbine, steam coming out of boiler expand in stationary nozzle. So if you can notice, there is a stationary nozzle, and its kinetic energy increases. And then if you can, okay, we will see one video so that you will get some understanding of it, that and this video will describe the difference between impulse and reaction turbine. Okay, so first we will look for the one video. Okay, so in the left side you have the impulse turbine, and on the right side you have the reaction turbine. Okay, so if you can notice over there, in the impulse turbine you have the nozzle, okay, the fixed nozzle, and then there are some plate, okay, that is in house in some casing, and these blades are basically moving blades. Okay, so if the steam flowing towards these blades, so as a result of impulse force, these blades rotate, and because these blades are connected to the shaft, and as a result the shaft also rotate. So all the blades that is mounted on the impulse turbine is basically rotating blades. And then if you can notice in the reaction turbine, okay, so first we will discuss about the impulse turbine. Okay, so these are the casing, this is the nozzle, these are the runner, and then there is a plate. and then this is the nozzle which sends some steam, and that is converted into high kinetic energy. Okay, and as your steam sent to your blade section, okay, so as a result of impulse force, all the parts of your blades which is connected to the runner will rotate. Okay, so this is just a basic principle behind the impulse turbine. Okay, now, and this is your generator, and as a result of this movement, so the generator will also rotate. Okay, so these graphs we will discuss after it, and now we will come towards the reaction turbine. Okay, so in the reaction turbine, basically we also have the nozzle, but that nozzle is basically mounted on some rotating shaft. And if you can just remember that the action and reaction force. Okay, so due to the reaction force, this nozzle, because this is connected to the rotating shaft, so this nozzle will rotate. Okay, so in this case, in the case of reaction turbine, we have the moving nozzles. Okay, so if you can notice that this will be rotating, and then in the impulse turbine, in the reaction turbine, we have two set of blades. First is the stationary blade. Okay, so if the steam that is coming from these nozzles pass through these stationary blades and then move towards the moving blades, so all these blades that are mounted, that is a stationary blade, will act as a nozzle. Okay, so in this case, your nozzle will be these blades as well. Okay, because these are the fixed, and when the steam passes through these nozzle, these blades, so these blades are also act as a nozzle, and this whole section will be called as a stage. Okay, because it is a combination of your uh, moving blade and stationary blade. So this is one stage, this is second stage, and this is third stage. Okay, so I hope you get some understanding. So now moving towards the lecture again. Okay, so now we'll continue from there. Okay, so this figure we already discussed. Okay, so this steam then impinges on the curved blade mounted on the periphery of the rotor. Okay, so this we already see as the steam glides tangentially over the blade, its direction is changed, changing its momentum. Okay, so if you can notice that steam is coming in from one section of the blade, okay, and it will glide and from the blade section, that is the curved section, and then it will come out. Okay, and due to these motion, there will be impulse force in this direction, and your blade will move, and this produces impulsive force on the curved blade which make the rotor to spin rapidly. Okay, so this is the important point over there. In impulse turbine, total expansion take place in the steam nozzle only, hence pressure remains almost constant while moving through the blades. Velocity of steam rises in the nozzle and fall while passing through turbine blades. Okay, so if you can notice that there is a diagram which is shown over there, that there is a nozzle, and from this nozzle there is some fluid coming out, and due to this impingement of fluid to the blades, your rotor, or you can say your blades will move. Okay, and as a result you can get some rotary motion. Okay, so if we can just take a look from the section point of view, that this is the section, and this is your nozzle. Okay, for example, if you can say that these are some nozzle from where your fluid or steam is coming in, and this is your blade, that is the moving blade. Okay, so we can say this is the rotor. The moving section is called rotor and your stationary section is called stator, okay, in this case. And if we can just take a look for the one graph, okay, so the graph which is mentioned over there. So in this graph, if you can notice that as your there's two curves, which is one is showing for the pressure and one is showing for the velocity. So for example, if I can just take a look for this section, that is from the nozzle. Okay, so as your fluid is passing through the nozzle, okay, so your pressure decreases, okay, at the end of the nozzle. So this is your end of the nozzle. So if you can just correlate with the figure above, so this is your end of the nozzle, and when your steam reaches towards the moving blade, so the pressure become constant, okay, as it moves towards the rotor section, or you can say moving blade. Then if we can just take a look for the steam velocity, so at the end of your nozzle, okay, so this is the point where there is an end of the nozzle, okay, or you can say end of the stator. At this point we have the maximum velocity, okay, and then as it moves towards the rotor section or moving blade, so it decreases gradually, okay, and your graph become like this. Okay, so this is just a basic graph for your impulse turbine, how your pressure and steam velocity behaves when it's moved from the nozzle to your moving blade section. Okay, so if you have any question you can ask me and then we will move towards the, because these are the important points over there. Okay, so this is just a simple graph. Okay, in the previous section I just take the fixed nozzle and the moving blade graph. So now if we can just look for the moving blade section graph only. Okay, so from this part, if we can say that this is your moving blades, okay, so which is shown over there, and from the moving blade, the pressure when it's the steam passes through the moving blade, so your pressure remain constant, and when your steam moving from the moving blade passes through the moving blade, so your velocity gradually decreases. Okay, so this is just a basic graph for the moving section of your impulse turbine. Okay, so now coming towards the reaction turbine. Okay, so just for your understanding purpose, so this is just a picture for your first steam device, okay, which uses the same principle that most of the reaction turbine uses. Okay, so in this case, if you can notice that once your steam will generate it, so this is a mechanism, okay, and inside this ball, or you can say sphere, there is a steam generated, and then there's two nozzles, okay, which is connected at the opposite sides, and due to the reaction forces, after there's a steam, so it will start rotating. Okay, so it will start rotating, and due to the, and this is just a basic principle for your reaction turbines cases. So reaction turbine work on the principle of Newton third law of motion, that is reaction force developed is equal and opposite to action force. So in this turbine, the rotation is caused by reaction force generated by momentum change of fluid. So here it is mentioned over there that first reaction turbine was demonstrated by this person and in 1883. So this is just a look for your first reaction turbine, and it consists of the radial tubes which are connected to supply tube and are free to rotate about the vertical axis, and the end of each radial tube is designed as a nozzle causing acceleration of fluid through the radial tube, and the rate of increase in momentum of steam along flow in radial tubes is provided by force on the steam from the nozzle wall in the direction of steam flow, and an equal and opposite force act on a nozzle wall causing the tube to spin around in a direction opposite to the steam flow. So this is just a basic principle behind the reaction turbines. Okay, so you just have to go through these theory so that you get some understanding of it. So now the same graph that we discussed for the impulse turbine. So now we will see for the reaction turbine as well. So in the reaction turbine, also we take two blades section, that is the stator and the rotor. Okay, but if you can notice that the main difference between your reaction turbine and the impulse turbine is basically the geometry of your blade as well. Okay, so in case of your impulse turbine, the rotating blades are mostly a cup shape. Okay, so for example, this is type of blade. Okay, and in the reaction turbine, your blade is mostly type of the aerofoil structure. Okay, and we will see the mechanism behind these blades as well. Okay, so if we can just take a look for the steam pressure and velocity diagram, okay, or you can say graph. Okay, so as your stator, so this is your stator section and your moving blade section. So these stator section basically act as a nozzle also. So for example, if you're at the end of your nozzle, so this is your end of the nozzle, so your pressure decreases, and then as it moves towards the moving blade section, it also gradually decreases. Okay, but in the case of the impulse turbine, it remains constant. Okay, and in case of reaction turbine, because there is structure of the blades are different over there, so your pressure also decreases in the moving blade section as well. And if you can look for the velocity, so at the end of your nozzle, the velocity reaches to maximum point, and then it decreases, okay, when it moving towards the when it passing towards the moving blade section. Okay, so this is the steam velocity and steam pressure graph for the reaction turbine. Okay, so here you can easily judge the major difference that in your impulse turbine, the pressure remains constant when it's moved towards the moving blade section, when the steam moves towards the moving blade section, and in case of reaction turbine, when steam passes through the moving blade section, your pressure again decreases. Okay, so this is just a basic difference of it. So in reaction turbine, in each row, that is a combination of fixed plus moving blades and is called as a stage. Unlike the impulse turbine, no nozzle as such are mounted in a reaction turbine. Actually, the steam is directed into moving blade by fixed blade design, accelerate the steam as the blade are unsymmetrical, that is the nozzle shape. So we are talking about the case of reaction turbine where the blades are unsymmetrical. So result is an increase in velocity over that of moving blades in case of reaction turbine, and these blades form a wall of moving nozzle that further accelerate the steam, and the steam acceleration in the moving blades result in a reaction of the blade. So this is just a basic theory behind your reaction turbine. Okay, and if we can just take a look for the pressure velocity diagram for the moving blade section of your reaction turbine. So from here we can easily figure it out the difference that for your moving blade section, your pressure decreases and the velocity also decreases. And in case of your impulse turbine, this graph is same same. So that it means your pressure is constant when your steam passes from the moving blade in the impulse turbine. Okay, so this is just a main difference between impulse and reaction turbine. Okay, so here is another comparison for your impulse and reaction turbine. So for example, if your impulse turbine, we have fixed blade, moving blade, fixed blade, moving blade, fixed blade, moving blade. Okay, and you can notice that your moving blade is the mostly cup shape in the impulse turbine, and in the case of your reaction turbine, your moving blade is almost like a aerofoil shape. Okay, and there is a fixed blade, fixed blade, moving blade, and fixed blade, moving blade. So we can just take a look for the velocity and pressure diagram for both of the cases, and we can just take a side by side comparison. So in this case, we already know that your pressure decreases at the end of your nozzle. So these fixed blades act as a nozzle. Okay, so in this case your pressure decreases, then as it moves from the moving blade section, so your pressure remains constant in the case of your impulse turbine. Then again there is a fixed blade, so pressure again decreases, then it's again constant when it's moved from the moving blade, again decreases, and then again constant for the moving blade section in the case of impulse turbine. And if you can just take a look for the absolute velocity diagram, that is your graph. So you can notice that at the end of your nozzle, your velocity is maximum, then it decreases. Okay, so then again it increases when it moves towards the fixed blade section, and then decreases. Then when it comes towards the moving blade section, then increases when it moves towards the fixed blade section, and then decreases when it's again come towards the moving blade section. Okay, so and if you can just compare with the impulse turbine diagram with the reaction turbine diagram, so we can notice that as the pressure, that pressure gradually decreases as it moves from the fixed blade section, then the moving blade section, and then again until it reaches with the end of the stage. Okay, and it gradually decreases. Okay, if we can compare with the impulse turbine and absolute velocity, the graph is almost same, but if you can notice that the absolute velocity is very small in the case of your reaction turbine, and the absolute velocity is high in case of your impulse turbine. Okay, so this is also one important point over there. So impulse turbine is characterized by the fact that it's require nozzle and that all the pressure drop of steam take place in the nozzle, and there is no pressure drop in the moving blade. So this is just a overlook of the. Okay, and since the pressure drop in the reaction turbine is gradual, okay, so as we noticed that the pressure drop will be gradual in the case of your reaction turbine as comparison to impulse turbine where pressure drop occurs only in the fixed blade, that is the nozzle. Across each row of the blade, fixed or moving, the speed is comparatively low in case of your reaction turbine, and more rows of moving blades are needed than comparison to the impulse turbine. Okay, so you can easily notice that if the speed is low, it means you are producing less power in the reaction turbine as comparison to the impulse turbine. Okay, so what has happened to this figure? Okay, so take a look for the comparison from. Okay, so if we can just take a look for the comparison between the impulse turbine and reaction turbine. So the steam is completely expanded in the nozzle and its pressure remains constant during its flow through blade passages. In the reaction turbine, the steam expands partially in the nozzle and further expansion takes place in the rotor blades. Then in case of impulse turbine, the relative velocity of steam passing over the blade remain constant in the absence of friction, and the relative velocity of steam passing over the blade increases as the steam expands while passing over the blade. In case of impulse turbine, blades are symmetrical. In case of reaction turbine, blades are asymmetrical. The pressure on both ends of the moving blade is same. Okay, as we look from the graph as well, that in the impulse turbine the pressure remains same, and in case of reaction turbine the pressure on both ends of the moving blade is different. The steam velocity is very high, and therefore the speed of turbine is high for the impulse turbine case, and in case of reaction turbine the steam velocity is not very high, and therefore speed of turbine is low. Okay, so these are just a quick comparison between impulse turbine and the reaction turbine. Okay, so till that point, if you have any question, you can ask me. Okay, and then we will just continue further. Okay, so now moving towards the main important point, that is the velocity diagram for the moving blade for an impulse turbine. Okay, so in this case, because whenever you have to analyze your steam turbine's blade section, okay, so the starting point is to draw the velocity diagram for the moving blade section. Okay, so in this lecture we will also look for that how to build the velocity diagram. Okay, so I will just okay, so coming towards again the velocity diagram of your blade, moving blade section. Okay, so in order to draw the moving blade velocity diagram, we can just and we have to draw the two diagrams, which is at the inlet and at the outlet. So, for example, this is the curved section of your blade, and we can just assume that this blade is moving with some velocity that is u. Okay, and we can start from the drawing of the inlet velocity diagram first and then towards the outlet. So this is your outlet, you can say this is outlet and this is your inlet. Okay, so for example I can say that this is your nozzle for example, and there is some steam that is coming out of this nozzle with some velocity. Okay, so I can say that this steam is coming towards your inlet of your blade with some velocity that is v1, okay, which is the absolute velocity we can say, or at the inlet. Okay, so here, because if you can notice that there is the velocity, you can say this is in the u. Okay, so we can say that this is the same velocity that is u. Okay, because the blade is moving with the velocity u, so you can also mark this velocity as a, so basically we are trying to draw the vector diagram. Okay, so this is your u, which is the blade velocity, and the angle between v1 and u, so you can say this is your alpha 1, which is the nozzle inlet angle, so you can mark it as a alpha 1. Okay, and then if there is a v1 velocity, that is the absolute velocity, so there is definitely a relative velocity as well. Okay, so you can say that there is one relative velocity that is at this point. So, and you can mark it as VR1. So this is your relative velocity towards the inlet. Okay, so now here another important point over there is, because as there is a v1, which is the absolute velocity, so there is two components of your absolute velocity. One is in the tangential direction and one is at the axial direction. So I can just mark one as, for example, as a tangential direction. So this whole we can call as a, so this is, we can mark as VW1. Okay, VW1 basically world velocity. So world velocity is basically the tangential component of your absolute velocity. So here we have the axial component as well. Okay, so axial component we can just draw a straight arrow and join this one, and the arrow will be upside. And this is your VA1, which is the axial velocity at the inlet. So one mean at the inlet. So alpha 1 at this angle, which is between relative VR1 and your world velocity, you can say, is the beta 1. Okay, so beta 1 is basically you can call as a blade inlet angle, but alpha 1 is the nozzle uh, angle made by the absolute velocity with the tangent of the wheel at the inlet. Okay, so alpha 1 you can say that nozzle inlet angle, and beta 1 is the your blade inlet. So this is the velocity diagram at the inlet of your blade. Okay, so here if we can just take the assumption that there is no friction, you can say in the curve area. So for example, at this area which is your curve, there is no friction. So the velocity that is at the outlet of your blade, that the steam of the steam velocity at the outlet of your blade, we can say that the same VR1, we can write that it comes out with some relative velocity which is VR2. So 2 mean at the outlet. Okay, and VR is the relative velocity at outlet. Okay, so here is the relative velocity. Now we have the V2 as well, because if there's a V1 absolute velocity at the inlet, so there is definitely one V2 velocity at the outlet as well. So we can say that there is one component. You can say this is your V2. Okay, and the same if V2, we have the axial component as well. Okay, so we can say that your VA2. Okay, the same VA1 is at the inlet, so VA2 at the outlet. So if we can just join these two ends, so this is the world velocity at outlet. So this is VW2. Okay, and the direction of arrow is in this direction. And then there is U as well. So U is the blade velocity. So you can see this is your U. Okay, so this is the vector diagram, and if we can just make some angles. So at the angle, so this is your alpha 2. Okay, so this is alpha 2, which is the nozzle outlet angle, and then or angle made by the absolute velocity V2 with the tangent of the wheel at outlet, and then beta 2 is your blade outlet angle. Okay, so this is the velocity diagram at the outlet. Okay, so and if we have assumed that there is a friction, okay, so for friction, we just have to consider another factor, which is the blade coefficient, which is basically ratio of VR2 divided by VR1 if we consider there is a friction. However, in this case, we are considering there is no friction, so we cannot need to consider this coefficient, that is blade coefficient, velocity coefficient. Okay, so this is the velocity diagram. So if you have any question, you can ask me, and then we move towards the next part as well. Okay, so I will suggest you have to draw this diagram by yourself so that you will get some understanding. Okay, and if you have to take some reference, so you can just take a look of this figure. So I have just drawn that the nozzle is at the bottom. Okay, so in this case, the nozzle is at the upside. Rest of the figure is almost same. Okay, and all the parameters that is mentioned, that V1 is the absolute velocity of steam, alpha 1 is the nozzle inlet angle, U is the blade velocity, VR1 is the relative velocity of steam at inlet, VW1 tangential velocity of steam at inlet, or you can say world velocity as well, and VA1 is the axial velocity of steam at inlet, beta 1 blade inlet angle, beta 2 blade outlet angle, VR2 relative velocity of steam at outlet, VW2 tangential velocity of steam at outlet, VA2 axial velocity of steam at outlet in meter per second, K if we consider there is a friction, and blade velocity coefficient is basically a ratio of VR2 to VR1, and then V2 absolute velocity of steam at outlet in meter per second, and alpha 2 is the angle made by absolute velocity V2 with the tangent of the wheel at outlet. Okay, so these all parameters are mentioned in this diagram, so you have to correlate with the inlet and outlet velocity. Okay, so now whenever we have to analyze some questions which are related to the impulse turbine blades or any moving blades section, okay, so we have to use both inlet and outlet velocity diagram in order to solve these examples, or you can say problem. Okay, but we cannot use as it is these velocity diagram. So what we have to do is we have to combine these two velocity diagram, which is the inlet and outlet velocity diagram combination. Okay, so we will draw one another diagram which is the combination of these two diagrams. Okay, so now we will take a look for the combined velocity diagram. So for combined velocity diagram, so I will just quickly draw the inlet velocity diagram. So inlet velocity we have already developed, which is this is your V1, this is your alpha 1, which is the nozzle angle, and then there is relative velocity. Okay, so you can make this line straight. So this is VR1 and this is beta1, and this section is your U, and this section is, you can say, VW1, and then there is axial component, so VA1. So this is the inlet velocity diagram. Okay, and a similar pattern we have to draw the outlet velocity diagram as well. So for outlet velocity diagram, so we can say that this is PR2, this is VA2, and then we have V2, and this is your VW2 world component, or this is your U. So this arrow is not over there, so this arrow will be in this direction. And then definitely there is angle, so beta 2, and then here is the alpha 2. Okay, so this is the velocity diagram at the outlet. So what we have to do is we have to just combine these two diagrams. Okay, so in order to combine these two diagrams, okay, so I will just reorientate it, okay, and to get some useful figure out of it. So for example, I can say this is your point, okay, and this is V1. Okay, so V1 come from the inlet velocity diagram. So V1 here, and then we have U over there, which is the blade velocity. Okay, and then we have VR1. So VR1, I can say this is like, and you have to use proper scale because the lines will be completely straight. Okay, so here we have VR1. Okay, so this come from the inlet velocity diagram. So, and now we have the world component. So the world component, you can say, was here, and then we have the axial component. So this is VA1, and you can say this whole is basically VW1, and the angle is alpha 1 here, and here we have, you can say, beta 1. Okay, so now this is your inlet diagram. So beta 1 we can draw off, right. Okay, so here this is the inlet diagram. So after this, we have to just put outlet diagram over this diagram. So for example, the velocity u, if you can notice, this u blade velocity is common in both outlet and inlet diagram. Okay, so we can say that if we can start from the u, so this u is basically common in both of your inlet and outlet velocity diagram. So from here, if we can just take one line from, and this is a straight line, okay, so we can say this is your VR2, and now we have V2. So V2 is basically, so this is your V2, okay, because U is common over there, and then we have the axial component at the outlet. So axial component, you can just draw a straight line over there. So this is VA2, and now if there is a world component at the outlet, so you can just draw VW2. Okay, this is VW2. Okay, so we have angle which is beta 2. Okay, so this is basically your combined velocity diagram for your um, analysis of your impulse turbine blades. Okay, so this type of diagram you can frequently see in your coming problems as well. Okay, so this is how we can generate the combined diagram by just combining inlet and outlet velocity diagram together. Okay, so if you have any question, you can ask me, or then we will solve some question so that you will get some understanding of it. Okay, so this is just overview of it. Okay, so you will easily find in any reference book as well. Okay, so this type of velocity diagram, but in each case, some of the parameters are just mentioned with the other units. For example, VA2 is mentioned with some other type of letters. Okay, so do not confuse over there. So this is just a combined velocity diagram. Just you have to combine both of the inlet and outlet velocity diagram, and you will get this type of figure as well. Okay, so by using this figure, okay, so for example, we can just take a look of it, and we have to find some parameters for this figure. Okay, so from this figure, if we can just take that this is your combined velocity diagram. So first equation that comes from this figure, if we want to find the tangential force. Okay, so in order to find tangential force, which component we need to require? We need the world velocity component. Okay, so for example, if we want to find the tangential force, then tangential force is basically mass per second. So mass per second multiplied by change in velocity. So you can say delta V. Okay, so mass per second, you can say mass. Okay, that is the mass coming out of your nozzle. Okay, so and then change in velocity, basically VW1, because whenever we have to find the tangential component, we have to use tangential velocity components. So tangential velocity components are VW1 and VW2. Okay, so this is the tangential component. So VW1 minus V. Okay, so another important point over there is, and also do not confuse this figure with the figure which I already draw in the previous slide. Okay, so only I have just make the orientation different from this. For example, if we can draw the I think outlet figure over there and inlet figure over there. Okay, and I have drawn inlet figure over there and outlet figure over there. Okay, so this is just a important point over there, so you can not confuse in this figure as well. Okay, so for example, your world component, so minus into minus W1. So why there is minus over there? Because if you can notice from the figure which I draw in the last slide, where I have just draw the VW1. So from that figure, VW1 at the inlet is in this direction, and at the outlet it is in this direction. Okay, so VW2. So from that figure, we can easily figure it out that VW1 minus, and this sign will be minus. So our tangential force become mass into VW1 plus VW2. So if we have the world velocity at inlet, world velocity at outlet, and mass per second given to us, so we can easily find out the tangential force. Okay, and your tangential force is basically contributes to the movement of the blade, and your axial force is required to find the flow rate. Okay, so this is how you can find the tangential force. So similarly, if we have to find the axial force, so force axial. So for this we require the axial velocity component. So we have to consider for VA1 and VA2. So from this we can easily find that the mass into VA1 minus VA2. So in this case there is no positive because the direction of VA1 and VA2 both are the same. Okay, so that's why there is no change in sign over there. So if we have the axial velocity component at inlet and axial velocity component at outlet and mass per second, so we can easily find the axial force. Okay, so here now we have the C. So C is basically work done by steam on blade. So work done by steam on blades. So here we can just write the equation. So mass per second, and then we have to use, because work done you can always find from the tangential components. So VW1, and here we have plus VW2, and now we have to multiply your blade velocity as well. So blade velocity is U. Okay, so if you can find out, so it will be in Newton meter per second. Okay, so if we have the mass flow, that is per second, and then work velocity at inlet, work velocity at outlet, and blade velocity, so we can easily find out the work done by steam on blades. Now there is fourth relation, that is to find the power developed by the turbine. Basically power developed, so this is also the power developed. So but it is in, if we want to convert it to kilowatt, so simply you can say that power developed is equal to M world velocity 1 plus world velocity 2 divided by 1000, and then there is U, so it will be in kilowatt. Okay, so you can easily find that this is your power relation. Okay, these relation you can just note it down because we have to use these relations directly in the problems as well. Okay, so you can note it down in this one and then we will continue writing more relations as well. Okay, so next relation, so we can say, which is the blade efficiency. So blade efficiency basically is equal to work done on the blade per second. Okay, so this means in watt, and then we have energy supplied to the blade. That is in also per second. Okay, so from this we already find the work done on the blade per second, which is m world velocity 1 plus world velocity 2 into blade velocity and energy supplied to the blade. So energy, where we have to get the energy. So we get the energy from the kinetic energy, and that kinetic energy comes from the velocity that is at the outlet of your nozzle. Okay, and for this we can just say that it is equal to energy supplied to the blade is half m v1 square. Okay, so if we have the value of or we can just simplify this equation as well, and we get that 2u Vw1 plus Vw2 divided by V1 square. So simply we can take this m out and we can just make this equation as 2u Vw1 plus Vw2 divided by V1 square. So if we have blade velocity, world velocity at inlet, world velocity at outlet, and V1 square, which is the velocity at the nozzle outlet, so we can easily find out the blade efficiency. Okay. So another relation, which is, you can say E and then F, which is the stage efficiency. So basically blade efficiency is related to the blade, and then there's stage efficiency. So stage basically is a combination of your moving blade and your stationary blade. Okay, so for this the equation become, so this is stage efficiency. So I'll just write stage SE, which is work done on blade per second divided by total energy supplied per stage. And from here, okay, you can note it down and go to the next slide. So your stage efficiency become that work done on blade per second, so which is m Vw1 plus Vw2 into U, and total energy supplied per stage. Okay, so at per stage, so because there is a heat transfer over there, okay, because if you can notice over there, so we have to consider the enthalpy's value. So the enthalpy values, that is between H1 minus H2. Okay, so this we will discuss also when we are going to solve the example where we have to get these H1 and H2 values if we require these for solving the problems. Okay, so these are just general formulas, okay, in order to find different parameters related to your impulse turbine blade. Okay, so I think you can just note it down till this point, and we will continue this lecture from next class. Because if I can